in the previous lesson, we gave a 0, 1 LP for the vertex cover problem. But we also saw that 0, 1 LPs are hard to solve, so that did not give us an efficient algorithm. What we're going to do now is take the 0, 1 LP, modify it a little bit using a very nice trick called LP relaxation, and that way get an approximation algorithm. Okay, so let's recall our 0, 1 LP for the weighted vertex cover problem. We have a variable for every vertex. For every vertex u, we have a variable xu, and the idea was that if this has value 1, then we decide to put it in the cover. If our LP gives it value 0, then we decide not to put it into the cover. Okay, and that gives us the following LP, where we want to minimize the sum of, well, the weight of a vertex times its variable, subject to, well, for every edge we had a constraint, and for every variable xu, we had an extra constraint saying that it was either 0 or 1. Okay, and then we had this algorithm. Okay, the problem was that this 0, 1 LP is hard to solve. So what are we going to do? We're going to what is called relax the LP. Or in other words, relax this constraint that it should either be 0 or 1. We're going to relax that constraint a little bit. And we're going to replace it by the constraint that xv should be between 0 and 1. Okay, so this new LP is called the relaxed LP. And, well, here this constraint that it's between 0 and 1, maybe the way it's written, it's not quite what is allowed in an LP, but of course I can rewrite this constraint as two constraints, one saying that it should be at least 0, the other saying that the variable should be at most 1. Okay, so this will give us our relaxed LP. And now after writing this or modifying this LP to get this relaxed form, of course we're going to solve this relaxed LP. Okay, and the nice thing is that now we no longer have this 0, 1 constraint, it's just a regular LP, and we can solve it efficiently. We can solve it in polynomial time. Okay, that's great. But of course we now have a slight problem, or maybe you could say a big problem, namely that, well, what are the vertices that we put into the cover, right? It used to be for the 0, 1 LP, it gives us either value 0 or value 1, telling us exactly whether or not to put it into the cover. But now we say that, well, these variables, they're allowed to have values 1/2, 2/3, anything between 0 and 1. And so the question is, how do we now decide which vertices to put into the cover? So that's what we're going to do next. So deciding which vertices to put into the cover, or maybe in the LP, you could also think about it as the variables now have fractional values, and we want to decide whether we are going to make them 1 or whether we're going to make them 0. So that's called rounding the solution of this relaxed LP. So let's see how we can do that. And there's different schemes, and we're going to just look at the simplest scheme, where we're going to take some threshold value t, and we have to think carefully about what is the right value of t, and then all the variables whose value is at least t are going to be put into the cover in our solution. All the variables that have a smaller value are not going to be put into the solution. They are rounded to 0. The ones at least t are rounded to 1. That's one way to think about it. Okay, so how do we pick this threshold value t? Well, I claim that for this particular problem, and for other problems we may have to pick a different threshold value t, but for this particular problem it's good enough if we pick t to be 1/2. Why is this the case? Well, what I want is that the solution that I get after I round my variables, that this is a valid solution, so that this is a cover. Okay, what were the constraints that we had to satisfy? Well, for each edge, uv, xu plus xv is at least 1. Well, if this is the case, if this sum is at least 1, then obviously at least one of the two has to be at least 1/2. Otherwise the sum would not be at least 1. So that means that after solving this relaxed LP and getting a collection or getting values for my variables that satisfy all the constraints, then I know that for each edge, one of the two variables, at least one of the two variables, is going to get a value of at least 1/2. So that means that this threshold will make sure that I get a correct cover for my graph. So, what's the final algorithm? Well, it's going to be pretty much the same as before, what we saw. Right? We have the input graph, then we write the LP, but now we take the relaxed LP, where we do not have the constraint that each variable is 0 or 1, but each variable is allowed to be between 0 and 1. Then we solve the relaxed LP in polynomial time, and now the cover C is going to consist of all the vertices whose value is at least 1/2. Okay, this algorithm runs in polynomial time because it's a normal LP. We can solve it in polynomial time. But the big question is it actually a good approximation algorithm? And that we will see in the next lesson.